going to study zero order, first order and half-life of our reactions. Okay. Now first let us discuss more what is zero order reaction. Okay. Or what is rate integrated rate equations. What are integrated rate equations? Okay. Now the differential rate equation, they depend on concentration. Okay. And the instantaneous rate, that is determined by the slope. Okay. At the tangent at point T. All right. In the concentration versus time plot. Okay. To calculate the instantaneous rate, we are using the tangent point. All right. On concentration versus time graph of instantaneous chemical reaction. Okay. The integration of different rate equation, it will give the value of concentration at different times. Let us see how this works. See, for zero order reactions, when time is equals to 0, concentration, it will increase. Okay. Right. Let us understand this integrated rate equation, which is different for each order reaction. Let us first do for zero order reaction. This is a graph for zero order reaction. All right. Now, in this type of reaction, the rate of reaction, that is directly proportional to the zero power of the reactant's concentration. The rate of reaction, it will directly proportional to this. Okay. Let us see an example where reactants, they are forming some product. Okay. Rate can be written as like this. For zero order reaction, we have written rate like this. All right. With the concentration of reactants at 0. All right. Now, as we use anything with power 0, it will become 1. It is equals to 1. So from here we can get the rate at the reactant side, the change in rate in the molar concentration of reactant with respect to the instantaneous time, it will become equals to K. Right. Now, if we integrate the both side of this reaction, if we integrate the both side, we will get this, and then we will find the rate of concentration. Let me, for first order reaction, in this type of reaction, the rate is directly proportional to the power first. Okay. As in zero order reaction, the rate is having direct relation with the zero order rate, right? Similarly, in the rate of chemical reaction for first order, okay, the rate of reaction, it will be directly proportional to the first power of reactant concentration. Okay. In a similar way, we are going to calculate the rate as we have calculated for zero order reaction. Okay. Here there will be a slight change as I have discussed with you for first order reaction in the last. Okay, where we are replacing this natural log value as 2.303. All right. Okay. Now let us understand the first order reaction rate with this example. Here is an example of hydrogenation of ethene into ethane. Okay, which is an example of first order reaction. Gaseous phase of reaction, where we have already discussed that the concentration, it will directly proportional to the pressure, right? So here rate constant, it will be as same value for as we have discussed for first order, right? It's like half-life of a reaction. Now what is half-life? The half-life is the time taken by reactant to reduce the concentration to half. Okay. Now for zero order reaction, it is given here for zero order reaction that the rate constant, it is the rate molar concentration of reactant at 0 minus the half molar concentration, right, divided by the time taken. This is the change in concentration of the reactants, right? Now if let us calculate for first order reaction here. For first order reaction, half life for first order reaction, it will be written as K is equals to 2.303, okay, by T as it given here, log R naught by R, okay, and R will be what? R will be what? It will be 1 by 2 R naught, right? So K will become 2.303 by T log into molar concentration of R naught by R naught multiplied by 2 according to this for half life. Okay, then T half, it will become 2.303 by K, that is the value of log, it is log 2. This will get cancelled, right, which is equals to 2.303 by K multiply log value 0.301, and that is equals to 0.693 by K. Okay, this is the value for half life for first order reaction. All right, and T half, it is as given here, it is independent of initial concentration, all right, of the reactant, right. Let us do one example here to calculate rate constant for first order reaction. Here rate constant is given, we have to determine the half life of reaction. So as we have just calculated half life period for first order reaction, that is equal to 0.693. Okay, for T half it was what, 0.693 by K. So K value is given, we are going to put the value and calculate the half life, okay, for first order reactions. Understood? Right. Now let us understand what are pseudo first order reactions. What does, now what is the word pseudo means? The word pseudo means false. All right. So what is pseudo's first order reaction? It states that there are many reactions which are of higher order, same as we discussed in order and molarity, okay, but it behaves as first order reaction. They are termed as pseudo order reaction. Okay, for example, here is the reaction given between ethyl acetate and water. Okay, now this is a pseudo first order reaction. Okay, it appears to be as higher order, but it actually is first order reaction, right? This is what hydrolysis of ester. This reaction is of hydrolysis of ester. Okay, ethyl acetate with water. It is forming acetic acid and ethanol. All right. Here, if we check the concentration at time T0, this is having 0.01 molar concentration and H2 is having 10 molar concentration. And in the product side, acetic at T times 0, it is having 0 mole concentration, and this is also having 0 mole concentration. Okay, which is the initial step. Now at time T, the concentration of this ethyl acetate, it decreases from 0.1 mole to 0. All right. And for water concentration, it decreases to 9.9 mole. That is only 0.1 mole of water is consumed in the reactor side, right? And the concentration of products on the right hand side, it decreases to 0.1 mole and 0.1 mole. Okay, so as you can see here that water is taken, okay, in excess, so it does not alter the rate of reaction. Okay, the concentration of water, it is constant here. That is why it does not change the rate of reaction, hence the order remains same. All right. Other example for this pseudo first reaction is inversion of cane sugar. Okay, what is the reaction for inversion of cane sugar? C12H22O11. This is the formula for cane sugar. If we do the hydrolysis reaction for, or say inversion of cane sugar, okay, in acidic medium, it will give us glucose, okay, and fructose. Glucose and fructose. All right. If I tell you to calculate the rate of this chemical reaction, it will be one order, K into H22O11, because this is a one-step reaction.